afternoon, everyone. Greetings to all of us. Previously, I would like to introduce myself. I am Rizqia Afifatu Latifah from Physics Department of 11 Maret University. On this occasion, I will present the research with the title Extraction of High Purity Nickel from Spent Nickel Catalyst for Cathode Material Lithium-Ion Batteries Nickel Manganese Cobalt. So, here is my presentation outline for today. And the first is introduction. Nowadays, the use of electric vehicles has increased as shown in this graph. The increase, the increase is continuous from 2020 until 2030. This is because the electric vehicles are considered environmentally friendly. The increasing use of electric vehicles has led to an increase in battery usage. According to the graph that's shown on the screen, the demand for batteries began to rise from 2020 until 2030. Lithium-ion batteries are the type of battery that are often chosen and used to meet these needs because of its performance. Lithium-ion batteries has two electrodes, namely the cathode and anode, which are separated by electrolyte. Electrodes that play an important role in the conduction of ions and electrons is the cathode. In recent years, an enriched nickel-manganese cobalt cathode has become one of the most widely used cathodes. Increasing the amount of nickel into the cathode can reduce the content of cobalt in the cathode. The result obtained is an increase in energy density and reduced production costs. As the demand for batteries increases, so does the amount of nickel needed to make cathodes, as shown in this graph. Nickel required for battery production has increased from 2015 until 2039. Therefore, an alternative source of nickel is needed considering that nickel is a non-renewable natural resource. One of the materials that can be used is spent nickel catalyst. Spent nickel catalyst is a byproduct of nickel catalyst that has been used and has decreased in effectiveness. Nickel can be obtained from spent nickel catalyst by performing nickel recovery process. So, the purpose of this study was to determine the effect of variation in the solid-liquid ratio used in the acid leaching process on the efficiency of nickel produced. And the second was to determine the, characteristics of nickel manganese cobalt obtained from recovery spent nickel catalyst on the capacity of lithium-ion batteries. Then the second outline is methodology. Procedure. The first procedure is the preparation of spent nickel catalyst. Spent nickel catalyst is crushed and then filtered using a sieve. After that, the lactic acid is heated to a temperature close to 80 degrees Celsius. The catalyst was added. The solution is heated and stirred. After 5 minutes, 30 ml of hydrogen peroxide was added. The solution was stirred for 3 hours at 80 degrees. When finished, the solution is filtered and the filtrate is testing using atomic absorption spectroscopy. And then the leaching solution is heated and stirred. Manganese sulfate and cobalt sulfate are added to the solution according to the calculation. Then the dissolve of oxalic acid was added to the mangan and cobalt leaching filtered mixture. And then natrium hydroxide was added until the pH is 2. After the temperature reached 80 degrees Celsius, the process is calculated for 2 hours. Then the precipitate was washed until neutral, filtered, and dried. After that, the lithium was added to nickel manganese cobalt. The material was mixed using a mortar and pestle, and then it was calcined at 500 for 6 hours, and it was sintered at 800 for 12 hours. Then the lithium nickel manganese cobalt was mashed and then filtered and characterized. The lithium nickel manganese cobalt was coated, and then the cathode is made, the battery is assembled and characterized. Next on the result and discussion. The leaching efficiency is shown in the table 1. Efficiency has increased at the variation of 20 grams liters and decreased to the variation of 30 grams liters. This happens because the solution is already at the saturation point. The highest efficiency was obtained from the variation of 20 grams liters, which was 65.47%. The next is the diffraction pattern of nickel manganese cobalt material. The peaks correspond to ICDG number 25-0250, and the sharpest peak is obtained at 2 theta 17 until 19 degrees. The, the crystallite size obtained is present in table 2. The crystalline phase of nickel manganese cobalt oxalate is the orthorhombic phase. The next is the result of characterization using scanning electron microscope. The resulting particles have agglomerate shapes with size that are not homogeneous. The particle in the largest size is owned by sample with the variation 10 grams liters. And then the nickel manganese cobalt material was also tested using Fourier transform infrared spectroscopy, and the following is the resulting spectrum. There are NEO hydroxide and carbon oxide bonds in each of the wave numbers listed in the table 4. This indicates that the material formed in the compound is oxalate. The next is diffraction pattern from the lithium nickel manganese cobalt material. The peaks correspond to GCPDS number 20-0781. The sharpest peak is obtained at 2 theta 41 until 43 degrees. The crystallite size obtained is presented in table 5. Lithium nickel manganese cobalt crystalline phase is a hexagonal phase with an R3M space group. The next is the result of characterization using scanning electron microscope. The resulting particles have agglomerated shapes with sizes that are not homogeneous. Primary and secondary particles have been formed, and the smallest particle size is owned by sample with the variation of 20 grams liters. And then lithium nickel manganese cobalt material was also tested using Fourier transform infrared spectroscopy. There are carbonate bonds in the wave number 900 and 1400. This is due to lithium hydroxide, which is easily changed to lithium carbonate due to the presence of carbon dioxide in the air. Then the electrochemical properties of the battery. The specific capacity and Coulombic efficiency produced are presented in the table 8. The highest specific capacity is 71 milliampere hour grams, and the highest Coulombic efficiency is 48%. The capacity and the Coulombic efficiency is still low because the lithium nickel manganese cobalt material has not been formed properly. The difference in particle size causes the ion diffusion process to be hampered so that there is a loss of specific capacity at the anode and cathode. Coulombic efficiency is still low because of the presence of a solid electrolyte interface layer in the first cycle of the charging discharging process. These layers can reduce the active electrode area so that in the next discharge process, the ion of lithium that returning to the cathode structure is less than the number that leaving the cathode. So that the Coulombic efficiency is less than 100%. And the last one is conclusion. From the research that has been done, it can be concluded that the highest leaching efficiency was obtained from the nickel recovery process from spent nickel catalyst with a solid liquid ratio variation of 65.47% from a ratio of 20 grams liters. The variation of the solid liquid ratio affects the leaching efficiency. Efficiency decreased at a ratio of 30 grams liters because it had reached the saturation point. And the second is the specific capacity produced from nickel manganese cobalt that match using recovered nickel is still low. The highest specific capacity obtained is 71 milliampere hour grams. Here are the references that I used in making this presentation. This research was supported by Professor Dr. Engineering Agus Purwanto, who have facilitated this research to completion. And we also acknowledge PT Petrooxo Nusantara, Gresik, for the catalyst used as the main ingredient in this research. That's all from my presentation. Thank you for the attention.